Hello, this is Group 1. Our project topic is Wikipedia image caption matching, and our group members are Yan Wenlong, Ye Jiaxun, Zhang Weixing, and Zhang Sai. There are 4 parts of our representation. Firstly, I'll introduce the project topic and the background. As the world's largest reference website, Wikipedia has more than 80 million content pages in more than 300 languages with over 80 million images. However, less than half of the images come with a caption text, and only 10% have some form of alt text. Therefore, we decided to build a model associating images with their corresponding image captions to increase accessibility and enable better research. Next, I'll introduce the dataset. The dataset is collected from the Wikipedia-based image text dataset, which consists of 37 million image text associations and in 108 languages and covering 11 million images. In practice, we selected the records with non-active values in important attributes that are useful for our models, such as the page title and the caption reference description. Here is an example. And this is the distribution of the top 20 languages. We can see that although the number of the text in English is the largest, other languages account for a considerable proportion. Thus, our model should be able to process text in many languages, which requires a universal pre-trained language model. As for the data cleaning, we discovered that file names of images usually contain useful and high-level summary information about the image. So we extracted the file names from the image URL. Most of the captions are combinations of phrases, so there is no need to do extra cleaning such as removing stop words or stemmerization. Here are some examples.
Next, we will dive into the detailed model. In these sections, I'm going to introduce the baseline of our model and its approved version with attention mechanism. Speaking of image caption matching, the first idea that came up into our mind is that can we convert the images and candidate captions into a common space like this so that we can compare them easily with cosine similarity? To achieve this, we need some feature extractors and encoders. So before we go to the baseline, first we will introduce 2 powerful tools in this project. We use convolutional neural network called EfficientNet, which uses a compound coefficient to scale all dimensions of depth, width, and this resolution of a network to become a feature extractor. It achieves better accuracy than previous convolutional neural network with fewer parameters and faster running speed. Also, it transfers well on transfer learning datasets, making it a very good fit for our task. Also, don't forget that this is a multilingual task, which means the language of captions are not just English, so we chose the XLM Robota to extract features from captions. Robota is introduced by optimizing the training of BERT architecture in order to take lesser time during pre-training. And XLM Robota is a cross-lingual version of Robota, which is pre-trained on tons of raw data which contains 100 languages, so then can be used to extract multilingual textual features for downstream tasks. This is our baseline. Basically speaking, the baseline consists of 2 pipelines. One is the image pipeline, and the other is the caption pipeline. They apply the pre-trained model mentioned before as the backbone to extract features from the image or text data, After that, two different fully connected layers work as encoders to represent the features as vectors of fixed dimension. Here comes my questions. What we ignore for simplicity when constructing the baseline is that the data provided in the challenge consists of files like image URLs, page titles, section titles, and so on. They are more than just the images and captions. We know that textual information from Wikipedia websites is highly relevant to the images, so that we might consider how to make use of those information for this problem. And we consider the image file name, which can be extracted from image URLs, will be helpful. Attention block similar to the self-attention block in transformers is then introduced into our model, since we want the file name as a query to conduct the representation of image features. Image features to be sent into the attention block as key and value need to be sequences. So it means that the convolutional neural network is now more suitable for this task. We use SWIM as the new backbone for image features extractors. SWIM transformer is a type of vision transformer with state-of-the-art performance in vision tasks. It can serve as a general purpose backbone for image tasks. And here is the new overall architecture. In the image pipeline, we use SWIM and XRM Robota as the backbones to extract image and file name features. The image features as key value pairs and output sequential embeddings of file name as query are sent into an intention block. The hidden layer state in the output of XLM Robota, taking file name as the input, can be regarded as a global feature of the file name, and it is sent to the third attention block as query.
Because of the challenge of large test set, about n plus 92,000 elements using a large transformer to calculate the relevance score for every query target part is infeasible, because we need to compute n square relevant scores to get the ranking for the whole test set. Thus, to release the computation complexity, we also tried another model. This model is a cascade of two different models, the multimodal caption proposal model and the caption rank model. In multimodal caption proposal model, the main idea is to represent the query and target data in a common feature space. The architecture of MCPROM model is shown in this figure. In this architecture, two main pipelines are the query pipeline and the target pipeline. A query is composed of image and image URL, while the target is caption. Thus, two textual and one visual fields should be processed in the model. In the visual field, clip is used as the encoder. Clip is a powerful multimodal composed of an image encoder and a text encoder chain to predict the correct visual textual pairings. Being pre-trained on a multimodal task, the image encoder module is a very good fit for our test. In the textual field, we do not use clip because the text is multi-language data, while pre-trained clip can only process single language data. Thus, in textual pipelines, we use a pre-trained large language transformer model, XLM Robota instead. XLM Robota has already been introduced before, and now I'm going to introduce another powerful tool, CLIP. While standard image models jointly train an image feature extractor and a linear classifier to predict some label, CLIP jointly trains an image encoder and a text encoder to predict the correct pairings of a batch of image text training examples. Then at test time, CLIP is a zero-shot classifier. CLIP converts all of dataset classes into captions, such as a photo of dog, and predict the class of caption. CLIP estimates birth pairs with a given image. And in MCPROM, in order to combine the features of image and image URL, attentive feature fusion is used in our work. Fusion module is composed of a subnetwork that computes two attention values, one for each query component. And the network is a simple MLP with a final sigmoid layer that takes as input the concatenation among the two input vectors U, which is image URL, and V, which is the image, and output two scalars alpha U and alpha V. After deriving alpha U and alpha V, the final query representation Q is calculated by the formula. In Caption Relang model, a pre-trained XLM robotic masked language model is used. It means that the encoder is a transformer model and the output of the CLS token is connected to a linear layer with an output size equal to the number of labels. The architecture is shown in this figure. The target of C-rank is to determine whether the image URL and the caption match. No visual feature is used in this model. After MMC Pro model process total n elements and derive the top k ranked elements, while k is much smaller than n, default is 1000 as candidate. The C-rank model used those k elements as a candidate and finally give the most matching 5 elements.
I'm going to talk about the evaluation part. We use a cosine loss function for our project test. This is the formula of the loss function. x1 and x2 are input tensors, and y is the tensor label with values 1 or -1. The input shape should be the embedding dimension. The reason why we use this loss function is because cosine embedding loss function is suitable for nonlinear embeddings learning, which is consistent with our project. For the implementation details, here is the related code. This is a test process for our model, which has attention blocks and has an image pipeline with swing as backbone. For each test case in dataset, we extract some features, IDs, mask, image, name IDs, and name mask. The squeeze process is just need to increase a dimension as batch size. After having these features, we input them into our trained model and have the corresponding two new output embeddings. Then we will calculate the cosine embedding loss of these two outputs. In order to show the test effect more comprehensively, we test all the 37,052 test cases and calculate the average cosine loss value. The average loss result is 2.72 E-06. This is a very low loss value, which means the matching ability of our model is good. For the MC prop model, here we conduct a 1000 multiple 1000 table. The table here is just a part of it. For each row, the column is sorted by the cosine similarity score, and the cell value represents the caption index. The higher the score, the higher the ranking. For example, for the first row, which has index 0, it matches the index 959 caption best, and then is index 0. The purpose of this table is to solve the huge test dataset problem. We only focus on these 1000 test cases, which will be used for classic C-rank model. This is all of our introduction to our project. Thanks for watching.